constructs of the theory of the Lorentz group, which can be relevant for solving problems of light polarization in the frames of the vector approach by Stokes and Mueller, and by the Spinor-Jones formalism. A definite correlation exists between completely and particularly polarization of the light and isotropic and time-like vectors of the Lorentz group. It is known that for completely polarized light can be described by Stokes' four-dimensional vector, or alternatively by Jones' complex two-dimensional vector. The Stokes four-vector formalism may be extended to a partially polarized light by Jones' approach does not. Here, starting from the Lorentz group theory, we introduce the concept of four-dimensional Jones spinor, first for a completely polarized light. To such Jones B spinor, there correspond isotropic Stokes four-vector and antisymmetric Stokes tensor. The last is equivalent to isotropic complex 3 vector. This approach is extended to the partially polarized light as well. We introduced corresponding four spinor of Jones type and four vector and antisymmetric tensor of Stokes types. We have introduced the concept of minimal Jones-like four spinor and have found relationships between the relevant Stokes vector and Stokes antisymmetric tensor in analytic form, which is studied numerically as well. The main line of evolution in theoretical methods of polarization optics seems to be quite independent of relativistic symmetry methods developed in the physics of elementary particles. However, it was noticed by many authors that these two branches of physics employ, in fact, the same mathematical technique, only with distinctions regarding notation and physical emphasis. The Jones complete formalism has close relation to the spinor objects of the Lorentz group. Keeping in mind the notable differences between the properties of isotropic and time-like vectors in special relativity, we should expect the same major differences in describing polarized and partly polarized light. And we begin from the Stokes-Mueller formalism. We see these objects A1, A2, A3, and we define the first two components in such form where amplitudes are positive numbers and phase shift delta belongs to the interval from -pi to pi. We have for these components such relationships in the form 1 and 2 for completely polarized light. The Stokes four-vector is an isotropic vector. For natural non-polarized light, we have such components, and after this, we can for partially polarized light can be obtained as a sum of natural light and completely polarized light in such form. With these notations for the Stokes four-vector, we have relationships in the form 4, and we see that this object have only value 0 or positive values, where big I is a general intensity, P is the degree of polarization which runs within in this interval. Now let us consider the Jones formalism and its connection with spinors for rotation and Lorentz groups. We start with relativistic two-spinor psi, representation of a special linear group SL, covering for the Lorentz group. We have vector psi in this form, where psi1 and psi2 contains the complex variable. And for this function b of k, we have such relationships. One may construct a two-rank spinor of the form, which can be resolved in terms of the Pauli matrices 6. The spinor nature 5 of C generates V with transformation for SA in the form 7. Let us introduce the Jones polarization spinor Psi, where N and M are amplitudes with these values, and we can represent our object in this form, where S1, S2, S3, and S0 have the form 8. Instead of alpha and beta, let us introduce the new variables, delta and gamma. Accordingly, the spinor Psi has the form 9, which coincides with the known Jones 2 spinor. The rank 2 rank B spinor U can be decomposed into tensors 10. We assume the two spinor Weyl spinor basics in this form, and the inverse relations have the form 11. After performing the needed calculation, we finally get relationship 12. In order that the vector and the tensor be both real, one should impose additional restrictions. First, constraint may be taken in the form 13. But unfortunately, we have the negative value for the S0. And because we will build the alternative constraint in such form. In this case, we obtain for S0 positive value, and also we have these expressions for other components vector S. The last case refers to the Stokes vector and two-rank tensor for completely polarized light because of the identity holds, identity 14. Similar isotropic conditions exist for two-rank Stokes tensor in the form 15. Existence of the Stokes tensor seems to be rather unexpected, and now we can examine our calculations. For this, we construct Stokes tensors from two-bank B spinor in the form 16, where for vector real has these components. And now, after performed needed calculations, we obtain following expression for the invariant in the form 17. And we see that this object has value, positive value, or 0. We conclude that such a vector SA can be considered as a Stokes for vector of the partially polarized light. Let us apply the following parameterization in the form 18, and then we get this expression for components of our vector, and the needed tensors are specified by the following parameters 19 and 20. Initial B-spinor may be represented as 21. Let us apply the simplest for spinor psi0. We can rewrite in the form 22. It uniquely determines the Stokes vector with such components, and the main invariant belongs to the following interval 23. Now we consider relationships between SA and SAB. It is convenient to introduce new parameterization for new four parameters A, B, C, D in such form, and we see that we can choose X and Y from the interval in the any way from the interval 0 pi divided by 2. Dependence of the spinor psi0 on non-measurable parameters X and Y is fixed by this formula, and the simplest way to restrict the freedom in psi0 is to set X equals Y equals pi divided by 4. In this way, we obtain the following equalities 20 in the form 24. Taking this in mind, we derive these equations where tau and sigma are new parameters. Representation for the Stokes tensor at these values X and Y with such notations is given by these formulas. The task is to relate angular variables which determine the Stokes for vector SA and for tensor SAB, and we have for SA two parameters tau and sigma, and for SAB four parameters rho, delta, mu, and nu. We start now with equations of the form. From the first, we express X and substitute into the second equation. And this equation leads to solutions, Y1 and Y2. Further, we find the corresponding X1 and X2, and let us collect result together in the form 26. This solves the problem of relation between the Jones for spinor and Stokes for vector in such way. Now we turn to Stokes tensor. Its components depend on four angular parameters. We see these parameters, and two parameters are presented in expressions for Stokes vector in the form 27, where tau and sigma are known from the above. So we can eliminate the variables alpha and s, and after needed calculations leads to these equations. So there arise linear relations, and exist only one free parameters in the difference beta minus t. All remaining are expressed through it in the form 28. In turn, four equations below provide us with solutions in the form 29, and in the above we derive the formulas for rho and sigma, Therefore, we find presentation for the main parameters of this difference in the form so T. The above relations between angular variables resolve the problem of one-to-one correspondence between the Stokes vector SA and Stokes tensor SAB for partially polarizing light. Thus, the partially polarized light, the Stokes bispinor was constructed for the first time, and a new concept of the Stokes tensor was introduced. For these objects, relationships between their components were found. And I want to add that in our work, we used the theory of Lorentz group, matrix theory, the relationship of second-rank spinors to tensors, and the theory of functions of complex variables.